In this lesson, we will define limits at infinity and horizontal asymptotes of a graph of a function. First, let's begin by reviewing the definition of a limit at a fixed point, a. Recall that the definition of a limit says that the limit of f of x as x approaches a equals the number L, and this is the notation, if the values of the function f of x get arbitrarily close to L as the values of x get sufficiently close to a but not equal to a. So the intuition, recall, is that the values of the function, which on the graph would be the y-coordinates, so the y-coordinates on the graph of f of x are getting closer and closer to height L as you take values of x very, very close to a on either side of a. So we're going to change this definition to discuss what happens when x grows very, very large. So we can define the limit of a function as x approaches infinity, or as x approaches negative infinity. But first, let's look at an example. Consider the function f of x defined as x squared minus 1 divided by x squared plus 1. Let's look at the graph. So the graph of this function is given by the blue curve below. Now consider the graph very far to the right. That is, when x gets very, very large, the graph of the function in blue is getting very, very close to height 1. And similarly, when x gets very, very large negative way out to the left, we see again that the blue graph is getting very, very close to height 1. So the function's values are approaching the number 1 when x gets very, very large, positive, or very, very large, negative. So we can define the limit as x approaches infinity of f of x to equal 1. So instead of letting x approach one single number, if we write x approaching infinity, this means what is happening to the values of this function when x gets really, really, really large. And we see that the values of these functions approach the number 1. We can define the limit as x approaches negative infinity of f of x to equal 1 as well, because when x gets very, very large negative, the values of this function are approaching height 1. So now let's give the definition of limits at infinity. So we're going to change our definition of limit as x approaches a to the following. We say that the limit of f of x as x approaches infinity equals L, and we write this limit notation, limit of f of x as x approaches infinity equals L, if the values of f of x get arbitrarily close to L as the values of x get sufficiently large. So again, the intuition is that the y-coordinates on the graph of f are getting closer and closer to height L as x gets really, really, really big. So on the graph, the limit as x approaches infinity would occur way out to the right. If the function's values are settling in at one particular height, at height L, then we say the limit of f of x as x approaches infinity equals L. Now conversely, if x is getting very, very large negative, so if you look way out to the left on the graph, we can define the following limit. We say the limit of f of x as x approaches negative infinity equals L, and we write this notation, x approaching negative infinity now. If the values of f of x get arbitrarily close to L as the values of x get sufficiently large negative. So on the graph of the function f, the y-coordinates are getting closer and closer to height L as x gets very, very large to the negative side. So look out way to the left on the graph and look to see if the function is settling at one height. So that would be the limit as x approaches negative infinity. Now consider the graph of the function y equals 1 over x. look far to the right on this graph. It appears that the graph is getting lower and lower and closer to height 0 as x grows very, very large. So in fact, we would write the limit of 1 over x as x approaches infinity equals 0. And to the left, we see that the function's values are getting very close to height 0 again as x gets very, very large negative. So we would write the limit of 1 over x as x approaches negative infinity equals 0. Now let's state some facts about limits at infinity. We developed all the limit laws for limits as x approaches a in an earlier lesson. Well, it happens to be true that all these limit laws are true when we consider limits as x approaches either positive infinity or negative infinity. So all the same limit laws apply. The limit as x approaches infinity of a sum would be the sum of the limits, and so forth. So all the limit laws follow as x approaches infinity or negative infinity. We just saw from the graph of 1 over x that the limit as x approaches infinity of 1 over x equals 0. Well, in fact, a stronger theorem is true. If r is any rational number that's positive, then as x approaches infinity, 1 over x to the r will always limit to 0. So in this fraction, as x gets infinitely large, 1 over any positive power of x will limit to 0. And similarly, if r is a positive rational number, and we can define x to the power r for all x, then the limit as x approaches negative infinity of 1 over x to the r also equals 0. So an expression where you have a power of x in the denominator, this fraction will go to 0 as x gets very, very large positive or very, very large negative. Now we define a horizontal asymptote. The equation of a horizontal line looks like y equals a number. So if you consider the graph of a function f, we say that the line y equals b is a horizontal asymptote of the graph of f of x if the limit of f of x as x approaches infinity equals b, or the limit as x approaches negative infinity of f of x equals b. So we see that if the function is approaching a horizontal line called y equals b, either to the right or to the left, either way far to the right or way far to the left on the graph, then this horizontal line is called a horizontal asymptote. Consider the graph we saw earlier of f of x equals x squared minus 1 over x squared plus 1. The function is getting closer and closer to height 1, both to the left and to the right. So the horizontal line given by equation y equals 1 is a horizontal asymptote of the graph of f of x. Consider the function f of x equals the inverse tangent of x. This function can also be called the arctangent of x. So this function looks like a very elongated S, and this function is interesting because it actually has two different horizontal asymptotes. Consider the behavior of the graph as x gets very, very large to the right. The function in blue is getting closer and closer to height pi over 2. So the limit as x approaches infinity of the inverse tangent of x will equal pi over 2. To the left, the function is approaching height negative pi over 2 as x goes to negative infinity. So as x gets very, very large to the left, very large negative, the inverse tangent or arctangent of x approaches negative pi over 2. So this function actually has two horizontal asymptotes. One horizontal asymptote is the equation y equals pi over 2, and the other is y equals negative pi over 2.